Hello friends, you are watching Arudire Plus, the professional CAD/CAM solution provider. Let's get started.
Welcome to the course CFD, a professional approach to solve complex industrial problems. Whether you are a beginner or intermediate learner, you must boost your knowledge and confidence from this course. In this video, I'll discuss the basic principles of computational fluid dynamics. It will be a brief introduction to CFD. Now, while talking about CFD, first thing comes to our mind is what is CFD or what is computational fluid dynamics? What does computational fluid dynamics mean? This means that in contrast to real flows, the flows can be calculated using computers. That means we can find pressure, velocity, temperature distribution, etc. and a lot more engineering parameters with simulation on computers. Like finite element method, in CFD also we are having three different steps. It is pre-processing, processing, and post-processing. In pre-processing, we have to model the object and then we have to apply appropriate boundary conditions. Now, what does modeling do? Modeling involves the continuous mathematical functions that we use to describe the real flow. But in reality, the flow is the consequence of the different laws of physics working together, all having the effect on the flow to limit computational effort. It is a matter of selecting only the ones with substantial impact on the flow that we are looking at. To avoid modeling errors, it is important to select correct and the relevant physical models. The most important model for fluid dynamics is the set of partial differential equations called Navier-Stokes equations. This basically describes and applies the laws of Newton to every small bit of fluid within the flow field, stating the dynamic balance between the forces acting on this small bit and the change in its momentum. This conservation of momentum together with the conservation of mass allows us to describe a flow field. There are analytical solutions. The entire flow field can be described using continuous mathematical functions. This allows us to calculate the pressure and the velocity at any given point within the flow field at an infinite solution. But for more complex cases, we don't have analytical solutions. This means that we need to break the reality into small blocks for which we do have a solution depending on the method. This can be finite element method or finite volume method. Here comes the term discretization or meshing. The process of breaking down a large continuous flow field into very small cells is called meshes. For each of these elements or cells, we can approximate the continuous Navier-Stokes equations with discrete algebraic ones. This allows us to calculate the pressure and velocity at the center of the element, also called node, based on the pressure and velocity values of the surrounding nodes. The higher the order of these discrete approximations, the more surrounding nodes are included. This reach of a single node is called the computational molecule, resulting in a set of algebraic equations for each node. The value of one node depends on the value of surrounding nodes and vice versa. These equations are connected, and to solve them, we need to put them all together into a big matrix. It is exactly like finite element method, and the big matrix is known as global stiffness matrix. Like finite element method, we are trying to reach towards the theoretical or perfect results, and the accuracy of the results depend on the degree of discretization or meshing. While discretizing based on the geometry, we need to select appropriate element from different types of elements. It may be a line element, a triangular element, or rectangular element. All are interconnected by means of nodes. Right? And the difference between the simulation results and the exact solution of the governing equations is known as discretization error. To have an accurate results, we need to focus on better meshing quality, because we know that better the mesh, better is the solution. To minimize the discretization error, we need to go on meshing and remeshing again and again till we reach the minimum measure. Right? Now the thing is, when we get the exact solution, then we can say that convergence criteria is achieved. Once we have defined our mesh and matrices with all the equations, we can solve them very easily. We can obtain the exact solution through direct method like Gauss elimination method or LU decomposition method. LU decomposition method is faster than Gauss elimination method, but sometimes it is very complex one. It is impossible to write a matrix in the LU form which is better known as lower triangular or upper triangular matrix. But this is a very complex one, so we need to solve these equations using computer with high level of accuracy. This is where the first order iterative method comes in. And in this method, they start by guessing an approximate initial solution. The longer we iterate, the more we converge to a stable flow field and more we reduce the iteration errors. The difference between the solution and the direct solution of the equation is called iteration error. So, to obtain an accurate computational fluid dynamics results, there are three different types of errors we need to keep under control. What are they? The first one is the modeling error, which is the difference between the real physics and the actual models. Right? Second one, what it is? The second one is the discretization error, introduced by chopping off reality and then approximating that into continuous equations with discrete ones. And thirdly, there is an iteration error, which is the difference between the exact solution of the governing equations and that one obtained via iteration. Now let me talk about its importance. Why is this so much important? Whenever we want to go for any kind of new product development, or you can say new technical project or research, definitely we need to go for different types of theoretical analysis, and then only you can get some results, right? But we are not confident enough that whatever results we're getting is right or not. That's why we need to validate our results with the experimental findings, and definitely there should be some with theoretical as well as results from software. But experimentation is not always possible because of some issues. The issues may be like different types of issues. The issues may be from economic point of view, or sometimes it may be from feasibility point of view also, right? So in this case, the software validation gets higher importance for the project. If we talk about software validation, CFD or computational fluid dynamics is one of the best tools because of its versatility and wide range acceptability. We can apply this one to inside our Earth or outside. Even in space also it can be applied by capitalizing the radiation effect of the sun. From application point of view, it has a wide range. It can be applied in different fields like aerospace, automotive, biomedical, chemical processing, HVAC and refrigeration, hydraulics, maybe oil and gas, power generation, and even in sports also it can be applied. We can solve any complex engineering problem with the knowledge of CFD. The main aim of this course is to strengthen your conception and to boost your confidence to solve any real-world engineering problem with CFD knowledge. This is a professional course made with lucid explanation and utter care, especially keeping in mind of the beginners. Hope you will be enjoying these videos, and I'm looking forward to see your comments. See you soon.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.